Hey guys and girls, welcome back to another video on this beautiful channel. On this beautiful day, we're gonna be making a kind of a pointer tutorial here. Now, I know I've done one of these before, and we've been going through a lot of pointer stuff in our other videos where we've been making dynamic arrays, all kinds of arrays, and just playing around with pointers in general, new and delete, dynamic allocation. But I noticed that a lot of people still have a bunch of problems with pointers. Now, I just want to make a firm kind of, what do you call it? Not a firm, but just a good pointer video where I explain how pointers work and the different type of things you can do with pointers and why they work and how it really looks. Now, I personally need to visualize stuff in order to learn, and I guess a bunch of other people need to do the same thing. So what I want to do for you guys is I actually just want to make a video where I show you what happens when you use pointers. Now, there's a few things I'm unsure about when it comes to arrays in the stack. I know how they work in the heap with new and delete, like our dynamic arrays, but with the stack and the static arrays, not really sure. But I'll give it a try. But at least with the pointer stuff, I'm pretty sure what happens. So let's just make a little stack here. Now I'm gonna make like a whatever, something like that. Just make like 4 or 5 of these. I'm gonna have to do the same thing on the other one, but because I'm a programmer and I'm really smart sometimes, I'm gonna do this, and I'm gonna cheat. I'm just gonna go ahead and do this. You know, just go ahead and just make me a cake for that. There we go. Bam. So yeah, okay. Now what we're gonna be doing is we're gonna give this some random addresses: 234, 235, 236. Sorry for the time this is taking. 237, 238. But trust me, we're gonna need this. 239. And for this, we're gonna say 5001. Whatever, like random numbers, you know. 5002 and 5003. That should be enough for now. And yeah, this should be good. Now, I'll be coding this as well, just as an example to show you what's going on, and I'll be writing stuff in here. So basically, imagine that we have a integer pointer. Now, we've done this before. We have an empty pointer here. We name it I. So it's an int pointer. It's stored here. It's really small. It's just a pointer. It doesn't have a start value or anything. Now, this isn't gonna hold anything. It's not pointing to anything. It's not, you know, it's just a invalid pointer, right? So if we made an int pointer here and we tried to call I, oh whoops, it would have some kind, it would have like undefined values, I'm pretty sure. Cout I and line, or if we tried to dereference it or something like that, it would have some weird values. Now, this is gonna print out the address of I. We're gonna see it breaks because it doesn't have a initial value. It's pointing to something weird. If we try to dereference it, the same thing's gonna happen. It's gonna crash. Bam. All right, that's not a good idea. So if we made this a null pointer, at least C++ would know that it's not pointing to anything. It's just there. You know, it doesn't crash anymore. It's just there. It's not pointing to anything, undefined. It's okay. But if you try to dereference it, it's gonna say it was a null pointer. I don't want to print anything out. So it's good. This is some kind of a safety net, basically. So what we did now is we didn't point it to anything. We just made sure it was a null pointer in here. Now, as you all know, we can put stuff in here. So integer. Imagine if we'll have two different cases. We'll just start off with this. I equals new integer 20. Now, this is called a stack, and this is the heap. Stack manages everything that is static, and it's just there from the start to finish. It's here. All the local variables in your functions and stuff, everything that isn't handled with new and delete happens here. Now, every time you do new, to make some dynamic memory allocation happen, C++ uses the heap, which is just a bunch of stuff where you can pop stuff and add stuff, and all kinds of stuff is happening here. It's just really chaotic. Now, when we do new integer, we'll put a new integer in here somewhere in the heap. with the value 20. With the size of an integer, the 20 and everything, just all the fat stuff is here. This is the slim kind of pointer. It just holds the address. Now what is going to happen when we point this integer to this heap location? What our pointer holds isn't the 20 or the integer, it holds the address to it. So 5001 is going to hold this address. Imagine this being the lifeline to this integer. If we lose this, if we start pointing I to something else, it's going to break. We're going to have a big problem because, or it's not going to break, but we're going to have I pointing to something else. This isn't going to go anywhere. It's going to be a memory leak. So we're going to lose this. This address is going to be lost. And we can't go back here because we're not sure which address it's still in here. Unless we point another pointer to this first and then change I. Then we're going to have something holding on to this integer here. But yeah, we made a new integer right there. Let's do that for ourselves here. New integer 20. Now remember, every time we do new, in the end, when we're done with that, we want to delete, just for the reason I just specified, delete I. So what that's going to do, when we're done with everything, we're going to delete I. Because we use new. For every new, we want to delete. Because it's going to remove this, and it's going to make I, not point to anything anymore. Well, not really. It's still going to be pointing here, but it's not going to have this value here. We're not going to get a memory leak. We can reuse I for some other stuff. But yeah, we have a new integer. If we just print out I, we're going to be trying 3 different scenarios here. We'll print out I, we'll use this operator, and we'll use this operator. Now I want you to guess before I give you the answer to what's going to happen in these 3 different scenarios. If we did cout I won't write everything out. Cout I, you don't need to write the end line here, and the address operator. What are these 3 different things going to print out? Okay, let's check this out. Let's try to run this first. It's going to print out, we need system pause basically. System pause. Sorry about that. Boom. Okay, so this printed out some humble jumble numbers. I don't know if that's a word, but this is an address basically. This is the actual value it's holding, and this is another address. All right? So what is going on? What is happening in our lives right now? This first thingy is going to print out this address to, this address, the one it's holding. Remember, the pointer is just like a regular variable. It's just, it doesn't hold values in the same way. It holds addresses. It doesn't hold regular values, but it holds addresses. So it's going to hold the address to the thing we're pointing to, which is 5001. If we print out the dereferenced I, which means this is basically saying print out what I is pointing to. So it's going to go in here, boom, to the address that it's holding, and it's going to print out our integer 20. Now, if we weren't pointing to an integer, or like a string or something, we're pointing to an object that can't be printed out, that doesn't have that printout cout operator overloaded. Basically, it's not going to be able to print it out. But I'm just saying, for integers and standard variables, this works. So it's going to print out what it's pointing to. Now, if this last one is kind of weird, it's like, the address to I, what is that? Isn't that 5001? No, it's not. That is 234. It's the actual address of where I resides, where the actual pointer lives. So that's the stack address. It's this one. And you're never probably going to use this, but it's still good to know what is happening and when it's happening. So the I is a regular variable which holds addresses to stuff in the heap or stuff in the stack as well. You can have an integer in here which is in the stack. You can point it to that. You can point it to another integer and stuff like that. And that's exactly what we're going to do now. So this is dynamic memory allocation. Now I have to remove this really, really carefully. Boom. We're going to remove all this as well. Okay. All this in here. We don't use this anymore. I am going to remove all of this. We'll keep this I here. And what we'll do is above this we'll make an integer a equals 50 or 409. Why not? It's almost like 50. So we'll do the same thing here. we'll keep I. We'll remove delete because we're not going to be doing this anymore. We'll just say a, and we'll make a new integer a equals, what was it, 409. It's like that. So we're pointing to a. Now this isn't working. Well, let me first show you why it's not working. We make an integer a in this address, integer a, which has the value 409. Now this isn't stored in the heap or anything. The int and its value is stored in the stack because it's a kind of a static kind of variable. It's not allocated with new or delete. You know what I mean. It's just there from start to finish in main. So it's in the stack. And we have our pointer, which we create later. Int I, the actual pointer thingy, and it's holding the address now to a, which is 234. Okay, just like that. It's holding this address. Let me make a new arrow. It's pointing to this, and what is happening is its value, well, no, that is, never mind. It wants to point to this, but a is 409. It's not a valid address, so we can't say that our pointer I is equal to a, but we need to access this address. Now, in the last video, in the last example that I just showed, we used this operator, ampersand operator, to get the address of anything which resides in the stack or whatever. So to get the address of a, we need to use that operator. So I is now correctly pointing to an address space or some address in the stack. So now we have 234. Otherwise, it would try to be 409, which is not a valid address, like I said. So this is gonna now correctly be pointing here, and the same rules apply. We'll be able to print out I, its address, print out what it's pointing to, and print out its own address. Now, let me see if this works. So we're printing out, see how they're kind of close? We're printing out the address of I, or which is holding 234, this one. We're printing out the value it's pointing to, and we're printing out its own address, which is a little bit away from that. And yeah, that's basically it. Now, if I'm correct, I'm not sure, printing out the address of what it's pointing to should be printing out I. It should be the same thing. It's the same thing. See that? Why is it the same thing? Well, the address of what it's pointing to is 234. And what it's holding is the address to what it's pointing to, which is 234. So it's the same thing. And yeah, that pretty much concludes the use of this I variable. Now, there's another way to do this. I could have just done this null pointer, and then I could assign I the address to a over here. You could do that as well. Now, I'm not using this thingy here because it's already created. Now, I used the asterisk here because I wanted to tell C++ I want to create a pointer. Here it's already created. Now, I is already a container of addresses, so I don't need to use the dereferencing thingy anymore. Dereferencing this would be pointing it to what it's, or trying to get what it's pointing to at this stage. So you don't want to do that. You'll just use I and stuff like that. Anytime you use this, it will be going to what you're pointing to. Sorry for repeating myself 1,000 times, but I think it's really important to get all of this stuff. Now, a lot of people ask me, before I go into stuff I'm not sure about, I'll go into stuff I am pretty sure about. A lot of people are confused about references, and why aren't references like pointers? What's the difference, right? What is the difference? Like if I made this into a reference, why can't I make that into a null pointer? Isn't this a pointer as well? It holds addresses. I mean, a reference holds addresses. Nah, well, it does, but it's not the same thing. Think of a reference as a constant pointer. You remember, if we make a constant integer b, it needs a value to start off with. You can't just leave it like this and make something out of it later. You have to initialize it from the start. The same thing with references. They're constant pointers. They need something from the start, which is valid. So I'll give it a. And wait, whoops. Why isn't this working? Let me see. Wait. Whoa. Now it's working. Okay, weird. But yeah, it needs to point to something. Now, we aren't using the address thing here because they're built to handle or work like regular variables. They're not like pointers in that way that you need to dereference them and stuff. This I is going to become a. It's going to become another alias for a. That's why we can't dereference it. Every time we call I, we're not calling the address of it. We're actually just directly referencing a, which is another variable. And the address to I and the address to a should be different. Address to a, they should be different, but this should be the same. A and I should be the same. So we'll try to print this out and we'll see what happens. So they're the same, the addresses. Okay, they're pointing to, well, this should not be the same, but they are the same. That's kind of weird. Or no, it's holding that address. I'm not really sure, but they're actually the same. Oh well, because I is a. Yeah, I becomes a, so it has the same address, I guess. Anywho, you can at least see that they're the same thing. That's kind of weird. Go check out stuff about references, but they're weird. They're a little weirder than pointers, but yeah, they need something to start off with. You can't just leave them, and they become an alias for the other object they're pointing to, basically. So yeah, I don't know what else to go through, really. I mean, if we made an array that is dynamic, it would store all that stuff in the heap, and it would go from, it would be ordered, basically, and it would point to the first object. So if we had an integer pointer I, and we said, like we're making in our videos, right? We're making these integer arrays. Integer array 2. Okay. I equals a new array of 2. What would happen is that I would be pointing, I would get the address 5001. Okay, let me just show you this quickly. I would get the address 5001, and we would have an integer array of 2 here. The first part of the array, first object in the array, would be here, and the second one, say it's 2, and the second one is 5. If we did that, I location 0 equals 2, I at the location 1 equals 5. It's like that, and then we'll say 4 2, or no, wait, delete I. Every time you delete an array, like we said in our previous videos again, you need to use these brackets here. But yeah, then we'll just delete it. So what happens is this is going to point to the first value, and then it's going to be ordered after that. So every time we use the indexing operator, it will know that it'll go to the next step, and we'll surely find the other object there, the next object in here. But what happens if we go try to access I2? It doesn't exist. It's going to try to go in here, the next ordered object, but there's nothing there. It's going to be out of bounds, and it doesn't. There's going to be an error. There's going to be a crash, all kinds of stuff. So don't do that. Stay in bounds and stuff like that. So yeah, let's see if we can print stuff out here. Let's see, cout I and line, cout the address to I and line, cout I0, and then cout I1. So let's see what this gives us. The address to I and the actual I is different because it's pointing to the heap. Now 2 and 5 is correct. What if we say the address to these two? They should be kind of ordered. They look ordered. I'm pretty sure they're ordered right here. See that these two are the same? The address to I, or what I is pointing to, it's pointing to the address of the first object. So they're the same. It's pointing to this, right? Just like this. So that's why this and this is the same. So this should show you a little bit how arrays work. If you're pointing to an array in the stack, this will be pointing to, it will hold a value, the first value here, and the rest will just come after it in the array. So it'll give you the same kind of values, but everything is going to be in the stack. Whew, I've been talking a lot. Sorry for rambling. I hope you learned something. Really just thank you for all the support. Thanks for sticking with me and helping me out, making the videos better. I got a lot of tips and stuff, so I'm happy about that. And I hope you're learning something. I know I just do this for your sake, basically. I like teaching. If I do it properly, I'm happy. Sometimes it doesn't really work out like I want to, but still, you know, I try. But yeah, this is really important. Keep learning about pointers. Try to get this in your head. Try to visualize all of this stuff. And yeah, thanks for watching again. Take care, and I'll see you in the next video. All right, bye bye.